Hello, welcome back to this channel. So today I'm going to talk about a new topic, which is hardness of materials. In engineering, hardness values are used for materials, and this is basically defined as a measure of materials' resistance to deformation. And this deformation is by indentation. So this is a measure of materials' resistance to deformation by indentation. By indentation we mean when we have got for example, a sharp object like this metal nail. This is a steel nail, and if this steel is going to touch any other surface, for example acrylic, this is a plastic, and if it is going to touch, then one of the material is going to deform. In this case, we know that steel is going to deform this plastic, and this we know by our experience that steel is hard material compared to this plastics. Therefore, the steel will make an impression, an indentation, if we push this steel against this plastic. So the property by which material shows its resistance to deformation in indentation is known as hardness of the material. So for example, this polymer, this plastic, is softer compared to this steel nail. So that's the reason why the plastic will get indentation if I push it. Other examples, for example, if I have got this wood, we know this wood will also get indentation if I push this nail against this wood. And again, this is because wood is softer and steel is harder. I have some other examples, for example, this brass. And now we are not sure whether this steel is going to produce any indentation on this material, because brass is also quite hard material. We know from our experience that brass is also quite hard material. So therefore we do not know whether steel is going to indent this brass or not. If steel cannot indent, and if we still push this, then this nail is going to deform. So that means brass is harder than this steel. So this is a kind of relative measure of hardness, and this becomes a property of a material if we are going to give a number to this hardness. And in engineering we need this hardness value for different materials, because this can be used quite conveniently for many other purposes. For example, we can relate this hardness to other properties like yield strength. So therefore, we can use hardness value to find out the yield strength. The other advantage with this hardness test is that it is a nearly non-destructive. That means when we conduct hardness test of, for example, this acrylic by using an indenter, and we press it against this acrylic, we are not going to damage this acrylic. All we are going to make is a small impression. So therefore it is called non-destructive test. Other advantage with this is, this test is, it is very simple, and very simple to get the value, and then we can compare those values and we can find out hardness of different materials and we can compare them. So these are the many advantages. So in this video I will show you what are the different types of hardness tests available, and what is the basic definition, how we define hardness in a more fundamental way. Other thing we should try to understand about hardness is the kind of deformation I talked about. So of course the material will undergo some deformation, but what kind of deformation it will undergo? And for the definition of hardness, we generally define as plastic deformation. So plastic deformation is a permanent deformation. That means the material will deform and the deformation will remain in the material. It is not going to undeform itself. But along with plastic deformation, there can also be elastic deformation. And we know that elastic deformation is recoverable. That means the elastic deformation can be recovered. And there can be also fracture. So although we define hardness by plastic deformation, but there will be some elastic deformation as well as fracture near the indentation. So this we should know. So the basic definition of hardness will be given like this. So in hardness we can indent using a spherical ball, or we can use any kind of shape. We can also use conical shape. So let's say if we use the ball and we indent on a material. So this is our material and this is the ball or sphere. So when we do the indentation, there will be deformation of the material, and the material will actually move, plastically deform, and it will make this kind of shape. And after indentation, we can look at the indent or the mark, and it will be circular in shape, because this ball is a sphere. So when a sphere indents a material, the mark left behind will be a circle. And we also know that there is a curvature here. So this has got curvature inside. So in the cross section, it should look something like this. So this is the indentation mark. So the definition of hardness is hardness as equal to the force that we have to apply to indent this material. So this ball is hard material. This is harder than this material. This is softer. So we have to apply certain force to do this indentation. So force divided by the area. And in the basic definition, we take this area as the projected area. So the projected area of this indentation mark is this circle. So we will get the area of this circle. So for example, if R is the radius of this indentation mark, then this area will be pi r square. Or we can just write area, because if the shape of the indenter is not ball, it can be any other shape. So in that case, we should just write the area. So this is the area, the projected area, which is left behind by this indentation mark. Now since the mark is left behind, it is permanent. So that means it must be the plastic deformation. So this projected area is representation of the plastic deformation in the material. So this is area of the plastic deformation. So this is the basic deformation of hardness of material. And the units of this one will be Newton, and this one millimeter square, and it can be given as megapascal. So basically unit of hardness is the unit of pressure. Megapascal is the pressure. So this is the basic definition of hardness, and by hardness we mean the plastic deformation, but there will be some elastic deformation as well as fracture. Now there are many different types of hardness based on some definition. Every inventor of hardness test has assumed some definition of hardness, and based on that definition he or she has proposed the hardness number. So for example, you must have heard about Brinell hardness number, BHN, or there is Rockwell hardness. There is also Vickers hardness. So there are many types of hardness numbers, and often they are given as numbers because they follow certain definition. So based on that definition, it is known as hardness number. So there are many types of hardness number which we will go through, but this is the basic definition of hardness, and if we use this definition of hardness, then we can relate hardness to the yield strength of the material. So yield strength by definition is a plastic deformation. So we can relate hardness to yield strength by this proportionality. So here we can say that hardness is equal to some constant sigma y. Now since this definition takes account of the plastic deformation, and therefore this definition of hardness is very much applicable to all kinds of metals, because almost all metals are plastic in nature, so they deform by plastic deformation. Most of the polymers or plastics also have this behavior, so we can use this kind of definition of hardness to find out hardness of metals and polymers. So let me explain to you further using my slides. So here I have written hardness of materials, but within bracket I have written engineering. So normally we are using this hardness test for engineering materials, but this hardness test is quite universal. It can be used for many other applications. For example, you can use for hardness of dental materials, biomaterials, or even food materials. So hardness is a very versatile test, and this is considered as an important property or mechanical property of materials. So as I said before, hardness can be used to correlate with some other properties like yield strength of materials. And the definition of hardness is a measure of a material's resistance to localized plastic deformation during indentation or even during scratching. But we can add that with or without elastic deformation and fracture, because many times we conduct hardness of very hard materials. In that case, fracture will take place. And the advantages of hardness has been listed here. It's very simple and inexpensive, close to non-destructive. Hardness data can be related to other mechanical properties of a material such as the yield strength. Both surface and bulk property can be measured, and it can be applied to all metals, most of plastics, and also ceramics. And this sketch shows a ball, which is a hard material ball made of hard steel or sometimes tungsten carbide or this kind of hard materials, is being pressed against another material of which we want to know the hardness. So when we press this ball against this material, there will be some indentation mark left. So capital D is the diameter of this ball and small d is the diameter of this indentation mark. Now let me tell you the classification of hardness tests. So there are many types of hardness tests, and I would like to classify them in this manner. So hardness tests of materials can be classified into 4 main types. First one is scratch hardness. As I said before, normally hardness is related to the normal indentation where a ball is pressed against a surface. But scratch hardness is also another type of test that we can perform. In this case, the indentation is produced on the surface as a kind of long line. So we produce a scratch rather than a small indent. And in fact, this scratch hardness or scratch resistance, as we call it, was invented the earliest, and it was invented in 1812 by Moe. So even today we can use Mohs scale, and Mohs scale is basically a comparison chart and hardness of all materials. Basically, Moe was interested in minerals, and therefore he produced a scale of 10 different minerals, starting with very soft mineral to very hard mineral. So the very soft one was talc. He used talc as a soft material, and very hard mineral was diamond, because we know diamond is the hardest material known to us. So talc has got scale of 1 and diamond has got a scale of 10. And between talc and diamond, he kept 8 other minerals of relative hardness. So as we go from one talc to the next 2, that means number 2 is harder than number 1. So that means the mineral number 2 can scratch mineral number 1. Similarly, mineral number 3 will scratch mineral number 2, and so on. So this is how Mohs produce a scale, and which is known as Mohs scale. And this basically tells us about relative scratch resistance of the material. This method is still used in mineralogy, where we have to find out the hardness of different minerals. It is also used for metals and polymers. Talking about relative scratch resistance, I will conduct a very simple experiment here to show you how it works. So for example, we have a acrylic, this is plastic, and we have got this nail which is hard steel. And if I scratch using this nail, you can see that this acrylic gets scratched. So if I push very hard, and you can see that this has got a scratch. So this is because this nail material is harder than this plastic, and therefore this nail can produce a scratch here. Similarly, we can see that on aluminum surface, if I scratch, so you can see that a scratch mark has been made, a straight line like this. So again, this material is harder than aluminum surface. Other material, for example, brass. Right now we don't know whether brass is harder or this steel is harder, but if I scratch it, then we will know if this nail is able to scratch this brass. We know that brass is softer than steel. So let's conduct this experiment. So if I press hard, and it makes a scratch. So we can clearly say that this steel is harder than this brass. Now I've got stainless steel here, stainless steel knife. So on this I will use this steel. Both are steel, but they are different types of steels. So let's see whether this nail material is harder than the stainless steel or vice versa. So this nail material is not able to scratch, to make any scratch, no matter how hard I press. So you can see that there is no scratch here. So we can say that this stainless steel is harder or almost equal in hardness to this nail material. So no matter how much I press, there is no scratch here. So either the hardness of these two materials are same, or this might be harder than the nail material. Similarly, if I have got a harder material like stone, and if I do the same experiment, actually it's not able to scratch, although it makes a line, but that line is because the metal or the steel itself is wearing out during sliding. So you can see that a line is made, but that line is because this material is wearing out. So definitely this steel is softer than this stone. So now we can see that using relative hardness concept, we can classify the material into very scratch resistant or softer. So this is the concept of Mohs scale for scratch resistance. The second type of hardness is known as shore hardness or durometer hardness. This one was invented in 1920, and this one was used for, or is still used for, rubber and elastomers. These type of materials show very large elastic deformation, and it will not show much of plastic deformation. Therefore, for this kind of material we need another type of approach, and in this approach basically an indenter is pressed against the material, and it is the depth up to which the indenter can go. That means softer the material, more will be the indentation depth. So based on the indentation depth, we can separate material, or we can define material which one is harder and which one is softer. But in this case, indentation is all elastics. So that means once the indenter is removed, the indentation mark disappears because the material regains its original shape. So this is one type of hardness. The next one is indentation hardness. So this is the usual hardness test that we conduct, and this is related to mainly plastic deformation, but also fracture can also take place. And the fourth one I would like to define are nano indentation. So this is a quite recent test. In 1992, the analysis for nano indentation was proposed, and this is based on the force and displacement data. So when an indenter is pressed against the material, as we apply force, the indenter goes deeper into the material, and this gives a curve which is known as force displacement curve. So force on y-axis and displacement on x-axis, and it will give a curve which is known as force displacement curve. And using this force displacement curve, it is possible to find out the hardness of the material. So in this video, I will only talk about indentation hardness, which is related to the plastic deformation. And this is the traditional method in which we produce an indent and we take the shape of the indent. This indentation hardness can be separated into two parts. One is macro hardness and another is micro hardness. So by name, it means where the indentation is in a macro scale, and here the indentation is in micron scale. So this is basically by using different types of forces we can produce these two types of hardnesses. So in the macro hardness, we have got Brinell hardness, Rockwell hardness, Vickers hardness, and Meyers hardness. So these are used in macro hardness. In micro hardness, again Vickers hardness, Meyers hardness, and noob hardness. Vickers and Meyers hardness, these are common to both, and just depending upon the load we apply, we can produce macro or micro hardness. So this is the way we can differentiate or classify the indentation hardness. So here in this classification, the Brinell hardness, Vickers hardness, Meyers hardness, and noob hardness, these are all based on the indentation mark. That means we have to image the indentation mark, and then we can find out the hardness number. The Rockwell hardness is slightly different. Rockwell hardness is very similar to shore hardness. Here we find out the depth of hardness, but Rockwell hardness is used for any hard material or plastic material, and in this case we first apply a very small load to adjust the depth, and then we apply the major load to find out the depth of indentation. And again, just like shore hardness, the softer the material, more will be the depth. So that is how we can separate the hardness data for different materials. So except for Rockwell hardness, other hardness tests are based on the indentation mark. Let me first talk about Brinell hardness number, because this was the very earliest hardness values, and this is used quite extensively in most of the metals industry. So, and this is based on the simple concept of pressing a ball of 10 millimeter diameter against the material, and this ball is either hard steel or tungsten carbide. So tungsten carbide is also a very hard material. So we use a very hard material so that this can indent the other material that we want to know hardness of. And after knowing the diameter of the ball and diameter of the indent mark, and this one is the top view of the indentation mark, and small d is the diameter of this indentation mark. So after knowing capital T and small t, we can find out the Brinell hardness number, which is written as HB, as equal to 2P divided by this equation, where P is the load in kg. So here, as you can see, this is a complicated equation, and this equation takes care of the curved nature of this indentation mark, because once we remove the ball, the material will have a curvature here. It will not be a plane. So because of this curvature, this equation or this expression takes care of this curvature. So this is how we define Brinell hardness, but this doesn't have any unit, so therefore this is represented as a number. We call it Brinell hardness number. Now Vickers hardness, this is also a number, because in this case also we do not give any unit, so this comes as a number. The difference between Brinell hardness and Vickers hardness is that the indenter shape is different. In this case we use a square pyramid as the indenter, and this shows a real indenter here. So you can see this, the tip of the indenter is a square pyramid. So once this square pyramid presses against a material, the impression that we will get will be of this type, a square. Now this square is the top view of the indent. So in reality the material has been pressed, so there is a indentation here, there is a depression here. So Vickers hardness number also takes care of the actual contact area between the indenter and the material, so which is these inclined surfaces. So therefore the area which is calculated is given by this formula. So here area is equal to D, where D is the average of these diagonal lengths D1 and D2. So D square over 2 sine 136 degree divided by 2, because 136 degree is the angle between two facing planes, which roughly comes to around D square over 1.8544. And the Vickers hardness number is given as HB, load divided by area, and this will be given as in this format. So this is the equation for Vickers hardness number, where L is the load that we apply in kg. Another important thing is that the force should be applied for 10 to 15 seconds, because every plastic material has got some time dependent response, which is known as viscoplasticity. So that means for the same load, if we apply the load for a long time, that indentation will be bigger than if we apply the same load for shorter time. So therefore it is important to standardize the time as well. So the time is defined as 10 to 15 seconds. So we should apply this load only from 10 to 15 seconds. Now depending upon how much load we apply, we can have macro Vickers hardness number or micro Vickers hardness number. Also there are many different types of scales depending upon the type of material. So for harder materials and for softer materials there are different scales, and we can use appropriate scales for Vickers hardness number. Now if the method of force application is by means of an instrumented device, then instead of dead load we will apply force in Newton. So previously I said about dead load, which is in kg. But if we are going to apply the force in Newton, so in that case the definition will be like this. We will use Vickers hardness number as equal to 0.18544 F divided by D square, where F is in Newton and D is the same average of D1 and D2. So earlier I said that the basic definition of hardness is the load or the force divided by the projected area, and therefore we can convert this Vickers hardness number into the basic hardness of the material, where we have the force divided by the projected area. And if we are using this square pyramid and we get an indentation mark of square like this, then in that case the area will be D square over 2. So therefore hardness is 2P over D square, where P is the indentation force in Newton and D is in millimeter. Then this value will be megapascal. So this will be based on the basic definition of hardness which is force divided by the projected indentation area. We can use the Vickers tip to find out the hardness of materials in megapascal using this equation and by measuring these two diagonals. Similar to Vickers hardness, there is another hardness which is known as Knoop hardness number. In this case also we used a pyramid, but the shape of the pyramid is slightly different. Here the adjoining faces have different angles, 130 degree and 172 degree 30 minute. So this kind of pyramid will produce a rhombus shape of the indentation mark, and it will have long axis and short axis. So in this case we can measure the long axis because long axis will be easier to measure, and we can find out the Knoop hardness by this definition, where P is the load in kg and L is the length of the indentation along the long axis, which is this one in millimeter, and Cp is a constant. So this is a simpler method because here we need to measure only the one indentation mark here. Knoop hardness is used generally for very hard materials or ceramics, for example ceramics or hard metals. So this is also a very convenient method, but again this gives us in the form of a number. So Knoop hardness number, although it can be related to other properties of the material as well. Now lastly I will talk about Meyers hardness test. This one was proposed quite early in 1908, and this method proposes that hardness is equal to load divided by the projected area of indentation, and this is what I called the basic definition of hardness. That means the load divided by the projected area of indentation, and if load is converted into force, then this will be the force in Newton divided by the projected area of indentation in millimeter square, and it will give us the hardness in megapascal. So the Meyers hardness is the closest to the basic definition of hardness, and this can be related to the yield strength of material, for example yield strength of metals and polymers. Here you can see that in this material an indentation has been made using the Vickers tip or the square pyramid, and we can measure the diagonals, and then we can calculate the projected area of this indentation mark, and if we know the force then we can find out the hardness. So this is how we can find out hardness of different types of materials, not just metals but polymers, dental materials, bones, different types of biomaterials, food materials, and so on. So by now I hope you have understood about hardness of materials and the basic definition of hardness, which is the force divided by the projected area of indentation. So using this method we can find out hardness of different types of materials, and generally we use the indenter, something like this, a very hard material with a sharp tip, and we indent on the material and we produce an indentation mark. We can use microscope to measure the dimension of this indentation mark, and then we can calculate the hardness. So plastics or any kind of metals, for example this is brass, we can use aluminium is another material, we can find out the hardness of aluminium, or even different types of plastics, hard or soft plastics. So thank you very much for watching this video, and in the next video I would like to show you an actual experiment where I will show you how we can measure the hardness of materials using very simple indentation tests. So thank you very much for watching this video.